Hi, I am Srikanth Guduru. I am pursuing my Masters in Computer Science, belongs to Department of Computer Science. Today my topic is on timing analysis of a protected operating system kernel. This topic belongs to IEEE 32nd Real-Time System Symposium 2011. In this topic, I will explain about SCL for an analysis of worst case execution time. Worst case execution time is due to the OS that offers virtual memory and protected address spaces. So the reasons behind worst case execution time are combination of size, unstructured code, tight coupling with hardware. And now I will discuss about SCL4. SCL4 is the world's first verified operating system kernel, and the most important points in SCL4 are it never stores function pointers at runtime, it never passes pointers to stack variables, and there are very few nested loops within SCL4, and it has unbounded operations. SCL4 is based on the concepts of L4. L4 is a second generation microkernel. It provides virtual address space, threads, synchronous and asynchronous communication. SCL4 is an event-based kernel. Kernel uses a kernel stack irrespective of which thread it is servicing. Context switching between threads is performed by changing a variable pointing to currently running thread. The main properties of SCL4 are it will never crash or performs unsafe operations. SCL4 codebase is small. Codebase means source code of software. ARM version of SCL4 kernel has 8700 lines of C code and 600 lines of assembly code. Analysis was performed using Kronos 4.1 version. Cell4 control flow is more structured because of event-based model. And Cell4 comes with a formal mathematical machine-checked proof of implementation correctness. And in this slide you can see the image for the Cell4 proof. In this image we can see how SCL4 was developed. The L3, L4 are the second generation microkernels. By using them, developers have developed different microkernels and they have used different processors. So from 1993 to 2013 it has 20 years in between, and they have developers developed different microkernels like L3, L4, L4 MIPS, L4 Alpha, Hazelnut, Pistachio, OK, L4, Nova, and they have used different processors while developing these microkernels. The complete architecture has been changed from 1993 to 2013. It took 20 years to develop SCL4 from 1993, and we can see the name of the creators in the image. So from 1993 onwards, developers have used the API inheritance and code inheritance from the L4 microkernels. Blue arrows indicate the code and the green arrows indicate API inheritance. Now we will see the processor model that SCL4 runs on. So SCL4 runs on different ARM architectures and platform. ARM is very fast and more efficient because of its reduced instruction set computing. BeagleBoard XM platform with TIDM3730 processor. BeagleBoard is an education tool for the development of open source software. This processor has an ARM Cortex A8 core running at 800 MHz with separate 32 KB L1 instruction and data caches. CPU have hierarchy of multiple cache levels, and SCL4 uses L1 instruction data cache. In this slide, we will discuss about SCL4 system calls. In this image, we can see the estimation time and execution time of SCL4 system calls. SCL4 uses priority based round robin scheduler. In round robin scheduler, it is used in the operating system to schedule processes. In this process, time sensitive threads must be assigned highest priority on system, so they can run as soon as required. In SCL4, threads don't communicate with each other, they construct IPC endpoints. So in the second image we can see the description of the L4 SCL4 system calls. SCL4 call. This system call is used to perform inter-process communication. And SCL4 reply wait. This system call is for worst case scenario of system call. It is used to respond to most recently received message and wait for new incoming message. SCL4 reply and SCL4 wait system calls. They are one-time endpoints stored in thread control block. In this image, we can see the workflow of SCL4. It starts with SCL4 binary, and we will get two types of outputs. One is estimated worst case execution time and another is observed worst case execution time. So observed worst case execution time has less process. The binary code is sent to the processor called BeagleBoard XM processor, and then we will get the observed worst case execution time. For estimated worst case execution time, it has a process which we can see in the image. In this slide, we can see the images for computed worst case execution time versus observed worst case execution time for different event handlers like syscall open, syscall closed, unknown syscall, undefined instructions, page fault, interrupt. So the ratio between computed worst case execution time and observed worst case execution time is highest for undefined instructions and then unknown system call and then page fault. In the next image we can see different functions in the SCL4 that took longest time to analyze. ARM underscore SY underscore syscall is assembly level entry point for all system calls. All other all other functions within the kernel are solved much faster. Till now we have discussed about the SCL4. Now in this slide we can see the similar applications like SCL4. There are three types of kernels which are similar to SCL4. They are RTEMS operating system, OSC Delta operating system, and microkernel operating system to kernel. First major static worst case execution time analysis of a real-time executive analyzed by Collin and Poat by using RTEMS operating system. OSC Delta operating system. OSC kernel permits interrupts in most kernel code except disabled interrupt regions. In microkernel OS2 it is analyzed for worst case execution time for each system call. In this slide, we will discuss some important features related to SCL4. The present day SCL4 uses hardware like ARM version 6, version 7 for 32-bit and version 8 for 64-bit cores. It has PC99 x86 cores for 32 and 64-bit mode, RISC-V RV64-bit cores. So this is related to hardware. Now we can discuss about device support. SCL4 runs on all device drivers in user mode. Device support is not the kernel's problem. SCL4 supports multi-core. In 64-bit processor it has ARM V7 32-bit and version 8 64-bit. The SCL4 used in multiple applications. The main targets are embedded systems with security or reliability requirements. For example, SCL4 is used in financial, medical, automotive, avionics and defense sectors. In this slide we will discuss about the challenges that are faced in SCL4. The main problems are the challenges that are faced during the development of SCL4 are adoption of the software verification, lower cost approaches for verifying the non-kernel parts, high level security, timeliness of complete real-time system. After analyzing this topic, I have got a doubt. Is formal software verification sufficient to say SCL4 is the world's most advanced kernel? Because it is the first and only OS kernel with security proofs of binary code. In this slide, we will discuss about the strengths and weakness of SCL4. The strengths of SCL4 kernel are security, safety of time-critical systems, mixed criticality operating system, and it is the world's fastest microkernel. The weaknesses are optimization problem and integer linear programming. So what is next after SCL4? After SCL4, now the developers are looking for the verification of RISC-V kernel, and they are also working on 64-bit ARM version, multi-core and hypervisor support, verification of multi-core SCL4, and time protection. In conclusion, we can say that this topic discusses about the interrupt response time analysis of SCL4 microkernel. This is the first analysis to our knowledge of a protected operating system providing virtual memory, and SEL4 was the world's first operating system kernel with the proof of implementation correctness. These are the references that I used for this topic, and thank you for watching.